Hi guys, it's Kate. This video is an introduction to inverse trigonometric functions and should be done alongside the worksheet, which is worksheet number 11 found on the course website. It's not going to be exhaustive, but we'll do most of the problems together and talk about the underlying information behind them. Let's take a look. Start with number 1, the warm-up problem. Think of two different numbers, theta, such that sine theta equals 1/2. And I would love to remind you that theta is an angle measure or a distance traveled around the outside of the unit circle. So pause the video, take a couple moments, and see what you can come up with. Ready? Well, there are a lot of different ways that you can start this type of question. You could use trig triangles, or you can use the unit circle. Let's take a look at the unit circle, and I'm going to label the first quadrant of it with the significant sine and cosine values for pi over 6, pi over 4, and pi over 3. So here's my unit circle, and I have pi over 6, pi over 4, and pi over 3 labeled, as well as their locations in the coordinate plane. And I remind myself down here that for whatever angle measure I'm looking at, or distance traveled around the unit circle, counterclockwise from 1, 0, that distance is w, that the ordered pair that I end up at in the coordinate plane around the outside of the unit circle is going to be cosine of that angle measure or distance traveled and sine of that angle measure. And so when I'm asked to find two different numbers, theta, so that their sine value is 1/2, I realize now that I'm going to be looking at the y value. And right away as I look through this collection of points, oh, I see that that happens right here. I see that that happens at pi over 6. Excellent. Now this has challenged us to find two different numbers. And there are a couple ways to do that. One is to say, okay, if I'm at that location in the unit circle, my sine value is 1/2, which means that if I take a full lap from pi over 6, so effectively adding on 2 pi to that, both of those distances traveled or angle measures will have a sine value of 1/2. So there are two answers right away. I also noticed that if I placed a horizontal line at y equals 1/2, there's another point as I travel between 0 and 2 pi around the circle that has a sine value of 1/2. This is pretty clearly not drawn to scale at all. It was difficult to fit everything in. But as we're looking at this, it becomes apparent that there is another point on the left side of the circle in quadrant 2 where the same thing is happening. And this point is found if I travel pi counterclockwise and then pi over 6 in a clockwise direction, right? If I go from here all the way over here, but then I subtract off pi over 6. So that means that 5 pi over 6 also has a sine value of 1/2, and we could add any multiples of 2 pi to 5 pi over 6 and also find values for theta that have sine values of 1/2, just continuously adding. So any of those, pi over 6 plus 2 pi n, or 5 pi over 6 plus 2 pi n. The point is that there's more than one. Yes, there are an infinite number of values that theta could take on, such that sine theta was equal to 1/2, but being able to find two is really critical for our jumping off point for this particular lesson. Let's see how this fits into a greater context with number 2. Take a moment, read about this situation, which is actually real, believe it or not. There was a lawsuit with a New York lawyer who was working on the case of an elderly woman. She twisted her ankle while she was chasing her runaway shopping cart down a ramp outside a Manhattan grocery store. And the curb is 6.5 inches high. The flat ground from the edge of the curb to the end of the ramp measures 50 inches. And that is going to define how steep that ramp is, like how far out the ramp reaches from this 6.5 inch high curb. And so New York law specifies that ramps must have a sloping angle of no more than 5 degrees. So what does that mean? I'm going to help you out. Let me draw my curb and my ramp. Saying that the ramp must have a sloping angle of no more than 5 degrees means that whether you're looking at this angle right here Or if you draw a horizontal line right here and look at the angle between the ramp and the horizontal, neither of those, they're the same angle, by the way, neither of those can be greater than 5 degrees. Otherwise, the ramp would be too steep, basically. So the lawyer wants to know whether the construction of the ramp was in accordance with this law, and what equation must we solve in order to find the sloping angle of the ramp. Pause the video, give it a whirl, and then come back. Have an idea? Well, first, let's label where the sloping angle is. And let's see exactly what trigonometric value we know about. Well, given that we know the length of the side within this right triangle, because this is a right triangle, the curve gives us a right triangle. We know the side opposite, theta, the sloping angle. We know the side adjacent to theta, the sloping angle. And so tangent becomes something that's really, really valuable for us. We know that tangent of theta is going to be equal to 6.5 over 50. And so this is the equation that we need to solve in order to find the sloping angle of the ramp. We want to know what value does theta take on in order for its tangent to be equal to 6.5 over 50. And then, of course, the secondary question is that value more than 5 degrees? So it's questions like these that are the central premise of today's idea. We usually are trying to figure out, okay, here's an angle measure. What is its sine value? What is its cosine value? What is its tangent value? But this is the reverse of that. We have the tangent value, and we want to know what angle measure has this tangent value. Or in number one, we have this sine value. What angle measure has this sine value? And so what we're looking for is an inverse to the trigonometric function. Let's, before we continue on into the worksheet, take a moment and remind ourselves what an inverse function is. Now, as we look at how to invert trig functions, we need to remind ourselves of what trig functions themselves do. Well, trig functions take something, a number, as their input, and that number is theta. Usually we choose that Greek letter, but it could be x, it could be w, what have you. Whatever it is, it's the angle measure input, right? Or distance traveled around the unit circle, either one. And what those functions spit out is sine of theta, or cosine of theta, or tangent of theta, etc. Or maybe it's secant of theta, or cosecant. Whatever it is, it's the trigonometric function value as the output. And now, when we're trying to build inverse trig functions, we remind ourselves that inverting a function means swapping the input and the output. So for an inverse trig function, our input is going to be some trigonometric function value, and our output will be the angle measure that achieves that trigonometric function value. Let's write that down. So this is what it means for a function to relate to its inverse function. The output and the input are in different places, right? We have had experience with this with exponentials and logarithms. In beginning to think about inverse trig functions, we also need to remind ourselves what a function is, right? And this is the key part that makes trig functions very, very tricky to invert. Well, an inverse function not only needs to undo the effect of the original function, but it needs to be a function itself, right? First day or second day of class, a function was defined as a mapping that for every input, you have exactly one output. And this is where inverse functions for trigonometric functions become really, really difficult. Don't be worried. You just need to be detailed in your approach. So let's visualize the graph of sine. Now, the next thing I'm going to say is pretty specific, and so you may want to rewind it a few times. We know that inverse functions, like an inverse trig function or just an inverse function in general, reverses the effect of the original function. And so if the original function had exactly one output for every input, the inverse function also needs to have exactly one output for every input. But what that means is that the original function can't do the following. It can't achieve the same function value in multiple places, because there's no way for you to undo that and have exactly one output in the inverse function. This was the basis for what was called the horizontal line test. And the reason the horizontal line test works is because if the original function, before you try to find its inverse function, if an original function intersects a horizontal line more than once, you are creating a situation where if the inverse function will have multiple outputs for a single input and therefore not even be a function. Let's look at sine as an example. So you can tell right away that sine fails the horizontal line test an infinite number of times, in fact. This is saying a particular sine value is achieved in my picture at 5 different inputs. And so if I'm trying to find the inverse function, which would ideally give me the particular sine value and then give me one specific angle measure where this happens, that becomes impossible because sine fails the horizontal line test. I have 1, 2, 3, 4, 5 different places where a sine value is achieved. The same sine value is achieved. And so you might think to yourself, well, this isn't even this just sine's problem. This is cosine's problem. This is tangent's problem. This is going to be cosecant's problem, secant's problem, cotangent's problem because of the periodic nature of all these functions. How are we supposed to be able to create inverse trigonometric functions when the functions themselves, upon first glance, are not invertible? Right? I can't rewind the effect of sine, the function sine x, because there isn't just one angle measure where a particular sine value is achieved. There's an infinite number of angle measures where a particular sine value is achieved. And so this one output for every input gets broken in the inverse trig function if I look at the entire sine function and see that, oh, there are an infinite number of places where every single possible sine value is achieved. So I can't invert that function. I need one place where every function value is achieved. That's what the horizontal line test is saying. Because if I have one place where every function value is achieved, then I can invert. I can invert that function and answer the question, hey, what input generated this output? Right? Okay, so we have a strategy that we're going to use for sine and cosine and tangent. And so let's work through it. It's on the worksheet. We're going to do number 3. And we're going to see what we have to do in order to allow sine to be invertible. We want to make it invertible, but it's going to mean that we have to compromise, and we're not going to be able to use the entire function. We're not going to invert the whole function. Let's go back to the worksheet and take a look. All right, number 3. It says on the axes below, sketch y equals sine x, state the domain and range of the function sine x. So just these top 2 right over here, domain and range, and then give me a nice, well-labeled graph of sine x on there. All of it. Don't try and make any adjustments quite yet. Pause the video and then come back. All right, how's it going? Let's take a look. I'm going to put a graph of sine x in here, and I'm going to remind myself that 1 and -1, its maxima and minima, they're a little bit shorter. They're less than in magnitude pi over 2 and negative pi over 2. So here's my best attempt at a graph. All right, there's my best attempt at a graph of sine of x. Its maxima are happening at pi over 2 and negative pi over 2, 3 pi over 2 and negative 3 pi over 2. It's an odd function, and the outputs there are 1 and -1, and then the zeros are at multiples of pi. What is its domain? What are the possible inputs for sine of x? Well, that is all values, right? Any real number you can plug in there. And what's the range? What are the possible outputs for sine of x? Well, the smallest it gets is -1. The largest it gets is +1. Let's take a look at part B. It says we would like to define arc sine of x to be the inverse function of sine of x. Why can't we do that? Well, sine fails the horizontal line test. There is not a function value is only achieved at one place, so I can easily create an inverse function type of situation here. Function values are achieved at an infinite number of places. So like 1 is achieved at pi over 2 plus 2 pi n for where n is any integer. It's achieved an infinite number of times, right? So because it's achieved an infinite number of times, I can't then have an inverse function that right away tells me, hey, what angle measure achieves a sine of 1, and then only have one answer come out, because that's what a function needs to be able to do. So we can't do this because sine fails the horizontal line test. A given function value for sine is achieved in an infinite number of places, which makes inverting the function impossible. Now let's take a look at C. This is the interesting part that is the critical point on which all inverse trig functions hinge, basically. Can we restrict sine x to an interval on which it is invertible? Meaning, can we only look at a piece of sine x that does pass the horizontal line test, is invertible, and then invert that? And the answer is yes. Let's take a look. And of course, there are an infinite number of intervals that could have been chosen, but as a mathematical community, the entire world agreed on one specific one. I need to pick a chunk that's going to hit all of the values that sine can take on and pass the horizontal line test. What does this look like? Well, I'm just going to pick this little piece of sine of x right here. And if I just look at that piece, right, all values for sine of x have been achieved, and it passes the horizontal line test. So I'm going to write down here that yes, if I restrict it from negative pi over 2 to positive pi over 2, it will be invertible. Now I'm going to continue on to part D, even though it's on the next page, but I'm going to stay looking at this graph that I drew in A. So I'm reading off of D. It says, if we restrict sine x to this interval negative pi over 2 to positive pi over 2, then it's invertible. We are going to define arc sine, which is the inverse trigonometric function for this restricted piece of sine. And so let's give it a whirl. Try to sketch arc sine. There are two different ways. So one way that you may remember is to reflect the original function, the black piece of sine here, over the identity, y equals x. Or you can take a few different pieces that you know and find points, swap the x and y coordinates, and then graph that function. I'll give you a few moments. Take your time, and then we'll come back, and I want you to try to figure out if this is the piece of sine that we are inverting. What does that mean about the domain of arc sine and the range of arc sine? All right, whether you are sketching or by reflecting over y equals x, or you're inverting some points, these 2 points, labeling the endpoints of the actual interval, are a really big help to labeling the endpoints of the arc sine function. So since pi over 2 and comma 1 and negative pi over 2 comma negative 1 are going to be involved, we know that by swapping the location of those points, those 2 points will be involved in the inverse function. So that means I want to start at 1 comma pi over 2, and I also want to label negative 1 comma negative pi over 2. Now I'm going to reflect across y equals x, and you can imagine that y equals x goes something like this. So my arc sine function is going to look a little bit like this, and then go up here. Oops, it got a little too vertical for my liking way up there, so let me tweak it. There we go. Now the questions of what's the domain of arc sine? What's the range of arc sine? Well, the domain of arc sine is the range of sine on that interval, which is the same as more broadly. But the domain of arc sine is going to be the range of that black chunk of sine. So that's going to be from negative 1 to positive 1. And then the range of arc sine is going to be, well, it can't be the same as the domain of sine, right? We truncated it. We shrank the interval and said we're only going to look at sine from negative pi over 2 to positive pi over 2 so that it's actually invertible. And so that's the range of that black piece as opposed to the larger gray function is what the range of arc sine is. So this is going to go from negative pi over 2 to positive pi over 2. Now, let's take a look at what that means about the outputs that arc sine will spit out. How will it answer these types of questions about which angle measure has a particular sine value? That's what's next. So we're now at E, and it says if P equals arc sine of Q, how could you express Q in terms of P? Well, a reminder that the input for arc sine is going to be a sine value, that Q is a sine value, and that P is an angle measure, right? That was from when we talked about what are the input and outputs of trig functions and their inverse functions. So if we're asked, how could we express Q in terms of P? Well, if we actually computed sine of the angle measure, we should get the sine value out, meaning that sine of P equals Q. That's the relationship when you see that P equals arc sine Q. This is similar to a logarithm, right? A logarithm gives you the actual number, and then the output is what exponent do I need this to raise this base to get that number? Arc sine acts on a sine value. That Q is its input. And the output is going to be, hey, what angle measure has this sine value? So it says in words, arc sine Q is the angle, but it can't be just any angle. It's going to be the angle that lands within the range of arc sine that we deduced on the previous page. So it's going to be an angle between negative pi over 2 and positive pi over 2, including those endpoints, whose sine value is Q. So let's take a look at F. It says, what is arc sine of 1/2? This is building off of that very first warm-up problem that we had, which said, name two angles whose sine value is 1/2. And we had an infinite number of them. We had pi over 6, we had 5 pi over 6, and we added multiples of 2 pi to either of those. But now, arc sine of 1/2 is more specific, right? Let's take a look at the unit circle. So not drawn to scale. Here we have pi over 6 in our first lap around the unit circle. Here we have 5 pi over 6, and the question is, what is arc sine of 1/2? Now, arc sine is the angle in the interval from negative pi over 2 to positive pi over 2. Negative pi over 2 is down here, right? And positive pi over 2 is up here. So arc sine of 1/2 is going to be this angle right here. It's not this one. This 5 pi over 6 lies outside of the interval. So when you're talking about arc sine of 1/2, it is really specifically the angle in this particular restricted interval, which we restricted so sine could just be invertible, right? It's the angle in this interval whose sine value is Q. 5 pi over 6 is outside this interval. So arc sine of 1/2 is pi over 6. Arc sine is a function. It only has one output. Now, a little note about notation. The function arc sine can also be written like this, where you write in a superscript -1 in between sine and x. Now, it's really important that this is not the same thing as this, because when you take sine of x and you raise that to the negative first power, that's what this second one means here. That's the same as 1 over sine of x. That's cosecant. This is not the same thing, right? This notation is inconsistent. We're aware of it. We didn't create it, but you definitely need to be able to read it and feel comfortable with it. Note that for any other exponent, placing the exponent in between the trig function and the variable, or the input, I should say, is the same thing as raising it to that power, but not for the exponent -1. -1 is the only one that's different. I don't know why. It just is. This is one of those quirks that you just have to remember. If I did it, you can definitely do it. All right, let's take a look at this true or false. It's going to test us a little bit. It It's going to say, since sine of 11 pi over 6 equals negative 1/2, then arc sine of negative 1/2 must be 11 pi over 6. Take a moment, think about it, and come back. Okay, have you thought about it? It might seem really easy to just be like, yeah, if a particular angle measure's sine value is negative 1/2, then arc sine of that sine value is going to give me that angle measure. But that is not the case, right? Arc sine only returns angle measures that are between negative pi over 2 and positive pi over 2. 11 pi over 6 is not in that interval. 11 pi over 6 is not in negative pi over 2 to positive pi over 2. So this is false. Now, what would the actual arc sine of negative 1/2 be? Well, if pi over 6 had positive 1/2, right? Negative pi over 6 would give you negative 1/2. I'm going to try to draw this onto a unit circle here. Here are two places on the unit circle that have a sine value of negative 1/2. But remember that arc sine returns the one between negative pi over 2 and positive pi over 2. This one right here is going to be negative pi over 6. It is the reflection of pi over 6 down into the fourth quadrant in the plane, right? Because we had dealt with pi over 6 up here. This is going to be negative pi over 6. So this would be negative pi over 6 if we wanted to turn that into a true statement. Now, as I hinted at before, cosine and tangent are going to run into the same trouble we had with sine, failing the horizontal line test at every single function value because of their periodic nature. So we want to talk about what we restrict the domains to in order to invert them and create arc cosine, the inverse trigonometric function for cosine, and arc tangent, the inverse trigonometric function for tangent. So again, there you could really, as long as you picked an interval that allowed the function on that interval to pass the horizontal line test, that would be an invertible piece of the function. But as a mathematical community, we need to agree on what we've chosen for cosine and tangent. So now we agree on what arc cosine and arc tangent are going to be, what kinds of outputs they will spit out. So arc cosine is going to be the angle in the interval from 0 to pi. 0 to pi you can sort of look at a graph of cosine to get a feel for that. So you can definitely see that from 0 all the way down to pi, we touch on every single function value, and that piece is definitely invertible. So arc cosine is the angle in the interval from 0 to pi, whose cosine value is x. Tangent faces similar problems. Graph a quick sketch of the tangent function. And here we are going to pick the interval from negative pi over 2 to positive pi over 2, not inclusive of the endpoints because there is no tangent value there, to be the invertible piece. So this is our invertible piece, the restricted domain that we're going to use to define arctangent. So arctan is going to be the angle in the interval from negative pi over 2 to positive pi over 2, whose tangent value is x. Let's do the same detailed look at tangent. Cosine will show up on the homework, but tangent, it's worth a look. This is quite challenging. So the very first thing you want to do is graph arctan, and I have this sort of rather terrible sketch of what tangent looks like and the piece of it that we're going to invert. So take a couple moments and give a graph of arctan a whirl. All right, my first step was to draw just the piece of tangent that I wanted to invert. So these vertical asymptotes are going to turn into horizontal asymptotes in arctan. Then you can think about sketching by reflecting over the line y equals x. Here's what mine looks like. So what does that mean for the domain of arctan? What are the possible inputs for this blue piece? All real numbers, right? It stretches on and on horizontally in any direction. Now, the range of arctan is going to be the domain of the restricted piece of tangent that I had originally sketched. So that means the range is going to go from negative pi over 2 to positive pi over 2, not inclusive of those endpoints. All right, now that you have a little bit of practice with sketching and thinking about the domains and ranges of these various inverse trig functions, let's do just a couple of problems that get at some of the finer points around them. Turn to page 3. Take a moment, try 5A and 5B. Do you get the same answer or do you get different answers for each, and then come back to the video? All right, let's take a look. In A, we're being asked to find what arcsine of sine of 3 pi over 2 is. Now, of course, you want to move slowly and methodically, and you want to start on the inside and then move out. So the first question is, what's sine of 3 pi over 2? Well, sine of 3 pi over 2 is -1. You can use a unit circle to help you with that. Now the question has transformed, right? The question is now saying, what is arcsine of -1? Now, arcsine, though, gives you an angle between negative pi over 2 and positive pi over 2, whose sine value is a particular number. In this particular case, sine value is -1. So the question becomes, okay, which angle from negative pi over 2 to positive pi over 2 has a sine value of -1? The answer to that is going to be negative pi over 2. The original angle in here, 3 pi over 2, it lies outside of the interval that we restrict sine to create arcsine. So these two don't just cancel. So it's always interesting when you're looking at a particular angle measure that doesn't naturally lie inside the restricted domain of sine before we invert it. Arcsine of sine is not just going to cancel. Do not just like slash through these and say, oh, 3 pi over 2, the end. Move really slowly and carefully. And once you see that original angle measure is not inside the range for arcsine, you know that you need to proceed with caution. Because what happens over here? Sine of arcsine. Well, arcsine of 3 pi over 2. What is arcsine of 3 pi over 2? What do you think? Remember that this is a sine value that's fed to arcsine, and this 3 pi over 2 is greater than 1. So this isn't even a possible sine value. Arcsine of 3 pi over 2 says, which angle from negative pi over 2 to positive pi over 2 has a sine value of 3 pi over 2? Well, 3 pi over 2 is not achieved by any angle measure as a sine value. And so this in here is undefined. And the reason for that is no angle has a sine value of 3 pi over 2. So B's entire expression is undefined. Right? You can't take the sine value of an undefined number. All right. Now let's take a look at how we can use arcsine, arccosine, arctangent, whatever, to solve equations. So it says, find all the values of x in a particular interval, in this particular case 0 to 2 pi, such that sine of x equals 1/2, and give exact answers. All right, I've drawn both of them on the unit circle, and I'm basically being told that I can travel between 0 and 2 pi counterclockwise from 1, 0. So basically in one lap this way, how many times does that happen? Well, it happens twice, and that fits with my sketch of the sine function. So I can see both of those either in the unit circle representation of how sine behaves or in just the sine function. I can see both those points of intersection. And as we discussed at the beginning, a sine value of 1/2 is one of the special values, quote unquote, and is the sine value for pi over 6. So I know that this little piece in here is pi over 6, and I know that this guy right over here is actually, I go pi in a counterclockwise direction this way, and then I subtract off pi over 6. So this little piece over here is pi minus pi over 6. Or we can call it 5 pi over 6, right? That's the simplified form. And so what that's saying is that this right there is pi over 6, and that right there is 5 pi over 6, right? You can also see that sort of like pi and then subtract off the pi over 6 to get to that point right there. So those are our two exact answers. I'm going to write those down in a nicer way. Now the question is very similar in that it says find all values of x between 0 and 2 pi such that sine of x equals 1/3 and give exact answers. And 1/3 is all of a sudden not one of like the special values of sine and cosine that we know. And so to give exact answers, this hint says we will need to involve inverse trig functions. So let's draw the unit circle again. All right, I can see that in one lap around the unit circle, right, from 0 to 2 pi, I have this happen twice, where sine of x equals 1/3. And what's interesting is that it feels like, okay, I want to know an angle measure that has a sine value of 1/3. Well, that's clearly going to be arc sine of 1/3, but which one of these is arc sine of 1/3? Well, arc sine of 1/3, remember, is the angle between negative pi over 2 and positive pi over 2 that has a particular sine value. And so this one right here, that's going to be arc sine of 1/3. So this guy right here. So I have one answer already, arc sine of 1/3. Similar to before, where we were like, oh, hey, these two have a relation. I can travel pi around the circle, like whoop, and then subtract off pi over 6. The same thing is true here. I can travel pi around the circle and subtract off. I know that distance. This length is arc sine of 1/3, so I can do pi minus arc sine of 1/3 to get the other place. So this one right here, this is pi minus arc sine of 1/3, and that is this particular instance where that sine value is achieved. Let me like label everything, because this is y equals 1/3, and this is sine of x. Cool. So those are our two exact answers, and that is arc sine of 1/3 and pi minus arc sine of 1/3 as the two angle measures that have a sine value of 1/3 on 0 to 2 pi. I leave the last few to you to think about and practice on. Of course, if you have any questions, please don't hesitate to ask. These inverse trig functions take a long time and a lot of practice and a lot of care. You always need to be thinking with an inverse trig function, do I have a good input, or is it going to be this like undefined situation that we had up here? And do I have an appropriate output? Where is the output supposed to land? What interval does it land on? So really be cautious about that. Take the extra time just sort of slashing through and saying, oh, these two things cancel. They don't, right? Sine, when it's not restricted, isn't an invertible function. Sine on a very particular restricted domain is. So you have to be very, very careful. Same thing for cosine, same thing for tangent. Take your time. Whenever you make a mistake, really sort of zoom in on what was the error and how did it happen. And, take that knowledge with you. I'll see you guys soon.